Today we are very invite Zishuo Zhao from Tsinghua University to give this talk. We will talk about Markov semigroup with the quantum shape. Welcome.
Thanks for the introduction and thanks for the organizer of this seminar. So today I will talk. So can anybody hear? Everybody hear?
Yes.
Okay. So my topic today is about Markov semigroups, but with the tracing of quantum symmetry. So and this is a joint work with Professor Zishuo Zhao, and the archive recently uploaded here. So feel free to check it out. So right. So first I will talk about one parameter groups before I talk about one parameter semigroups. So here is the table of contents. So first I will talk about background on quantum Markov semigroup and its origin in physics. And then I will introduce the quantum Fourier analysis. So that is the hallmark of quantum symmetry. And in this framework, I will then talk about the module quantum Markov semigroups, and in particular, the how to formulate equilibrium states and GN symmetry in that case. And the final remark will be about some applications to functional inequalities. So let's first talk about one parameter groups. Maybe everybody here know that in quantum mechanics, the states of the system, if we are talking about closed system, is always described by some vectors on Hilbert space. And typically we have a self-joint operator called the Hamiltonian that drives the evolution of the system like this if you are in the Schrodinger picture. So you take e to the ith and you act it on the state. And know that e to the ith is a one parameter group of unitaries. So if you are more interested in operators than states, then you would like to form this rank quantum density matrix. And then the time evolution of this state in terms of as a density operator will be given by conjugation of this unitary. So you can see here that this is a one parameter group of star automorphisms. Now, but there are many other systems where it is not closed, and when it's not closed, it means that I have a subsystem in a potentially very big environment. So, and the environment and the subsystem as a whole has a Hamiltonian, but the Hamiltonian may involve interactions. That means that the state space is separated as a tensor graph, but the Hamiltonian of the whole system may not be factored into a tensor, sum of tensor vectors. So in that case, the time evolution will be quite complicated. But we can reduce that complexity by looking only for the subsystem itself. That means that we first evolve the state by this one parameter group, and then we take the partial trace, we trace out the environment. And this composition just gives us a trace preserving completely positive map. It's a very fundamental theorem of Sangster shows that every completely positive trace preserving map arises in this way. So in terms of states, in terms of the density operator, a quantum channel is just a completely positive trace preserving map. But it turns out that it's in some sense more natural and easy to make this extension if we formulate the previous feature using operator algebras. That is, we focus on the observables. Then the CPTP maps in the previous page then corresponds to completely positive uniform map. That means that trace preserving case corresponds to the fact that phi preserves the unit. So this is a equivalent way to say that phi is probability preserved. And if we further impose that so-called weak coupling limit, this means that the interaction, this basically means that the environment is large enough to be unperturbed by the interactions with the system. Then this formula will be reduced to, we will have the following Markov property. That is the second bullet point here. So if we first evolve for time scale s, and then evolve t, it's the same as we evolve t plus s. And of course, when nothing happens, when time at 0, we get identity. And with some continuity condition at t equal to 0, this defines a so-called quantum Markov semigroup. So just a family of quantum channels that satisfy this three. So in particular, if we go back to the closed system picture, this one parameter group of unitary, if we restrict t to be greater than or equal to 0, is the simplest possible quantum Markov semigroup. So to study a family of quantum channel, we need to first know how to represent a single quantum channel. And in terms of in the case of matrix algebra, this is given by the well-known Troy matrix. So given any quantum channel, and in fact, given any a completely positive map, you can form the Troy matrix as a matrix in MNC tensor MNC. And there is and here I have put opposite here because later we will align this with bimodules. So sorry for this. I forgot to change that. So in this algebra, this C5 will be a positive matrix, even only if the map phi is completely positive. And for a positive matrix, we can perform a spectral decomposition. Then you can use the Troy matrix and its spectral decomposition to determine the cross representation of any completely positive map phi in this way. And in particular, if phi is unital, and that means the cross operator, this ki, satisfies the constraint here. So ki dagger ki, some order I must be equal to identity. So once you know a single quantum channel, you also want to use the fact that we have a semigroup of quantum channel, not arbitrary one parameter family, but a semigroup. This means that the whole family can be characterized by the generator, and the generator is defined in this way. So yeah, you notice that the sign may be wrong, but later we'll say that this is a natural choice. So this 4 people, they proved that in a very general scenarios that the generator defined here generates a semigroup of quantum channel, or generates a quantum Markov semigroup if and only if L has the following form. So you can see a piece of unitary evolution here. In some sense, this H will be the Hamiltonian of the original closed system. And you can see something that is not quite a unitary evolution, namely this second part of this formula. So this terms, some people call this Li Lindblad operator, some other people call this cross operator, but this whole second part of the formula basically results from the interaction between the closed system and its environment. So if you only want to study interactions, you can forget about it. So the synthesis, if you only want to study the interactions, you can just forget about the unitary dynamics and just focus on this part, right? And so the following two semigroups, Markov semigroups are realized in this way, namely that there's no unitary dynamics at all. So one of them is the depolarization, and the other is just defacing. So defacing semigroup is basically you exponentially suppress all the off-diagonal terms, and depolarization is that you exponentially suppress all in all directions other than the identity. So these two forms the two simplest possible quantum Markov semigroups, other than unitary dynamics. Okay, so there's a concept of decoherence-free subalgebra, and this turns out to be quite related to the quantum symmetry that we will later talk about. So the definition of given a quantum Markov semigroup phi t, we can define the so-called decoherence-free subalgebra as a set of observable O such that there is no dissipation at all. So even though we can think of these are the observables that on the closed system, on the subsystem, even though there are interactions between the system and the environment, the observable itself only experience the unitary dynamics. So they are free from interactions of the environment. That's named decoherence free. So, and we can further impose that there's no unitary dynamics of the subsystem. So we impose that there are only interactions. Then you can show that the decoherence-free subalgebra in this case corresponds to the set of fixed points of the semigroup, or equivalently corresponds to the kernel of the generator L. And why this decoherence-free subalgebra is interesting, because once you know that, you will have a so-called bimodule property. This basically says that phi t, if you evolve x1, y, x2 for time t, then you can first evolve y and then multiply x1, x2 from left and right, provided that x1, x2 are decoherence free. So in some sense, decoherence free subalgebra is the largest possible subalgebra with respect to which the quantum Markov semigroup is a bimodule, is a semigroup of bimodule maps. And that naturally leads to the connection with quantum free analysis that we'll later talk about. So before that, we can look for instance, one of the simplest QMX, namely the defacing semigroup. In terms of the defacing semigroup, as we have seen, it suppresses all the off-diagonal terms. And that means that only fixed points are those diagonal matrices. Also, you can just check that L goes to 0, you can solve with it. And then you will see that decoherence-free subalgebra is a set of diagonal matrices. So a slightly more complicated scenario is where you can take the Lindblad operator or the cross operator to be the spin in direction x, y, z for a composite system of 3 qubits. Then it has an SU2 symmetry. So the turns out that the decoherence-free subalgebra in this case corresponds to the commutant of this SU2 action. And you can just decompose this Hilbert space into representations to find the structure of decoherence-free subalgebra. So in general, the decoherence-free subalgebra of a quantum Markov semigroup, provided that there is no unitary dynamics, will be the commutant of the algebra generated by the cross operator. Yeah, but of course, this can only works in finite dimensional case. And so what if the system may not be finite dimensional? Then that's where we have to introduce quantum Fourier analysis. So so what is QFA? It's a pictorial language that used for study of quantum symmetry, including quantum systems with symmetry. So this originates from the subvector theory, and in particular, the formulation of subvectors in terms of finite algebra. So so how exactly is related to decoherence-free subalgebra? So we may think a scenario where the system itself is infinite dimensional. It's described by the infinite dimensional object algebra, but and we have a quantum Markov semigroup. But that semigroup may have a relatively large part of decoherence-free algebra. So relatively large means that the decoherence-free algebra as a subalgebra has a finite index in the algebra of all observables. So one of the most important things in that quantum analysis can do in this case is that it provides a very natural definition of the Troy matrix, which previously can only be defined on finite dimensional systems. So so we can formulate the relatively largeness of the decoherence-free algebra in terms of lambda extension. So by that we mean we have inclusion of Neumann algebras inside M with a faithful normal trace tau on M. And we can, so this part is the standard procedure that which produce from a given lambda extension and M extending N to a bigger one that extends M. And it's called basic construction due to Jones. So so it's actual, the details may not, it's not very important, but the important thing is that we can have a notion of size. So this is basically called the Jones index of M over N, and you can think about it as the dimension of M as an N module, and it's defined in this way. So you can iterate the basic construction indefinitely many times, but in this talk we will just focus on the first two steps of basic construction. So the whole structure is called Jones algebra, and Jones axiomatized this structure in terms of finite algebra. But in order to study quantum Markov semigroups, it turns out that most of the structures are just contained in the first two steps. So potentially there are many new stuff beyond that, but at this point it seems so we haven't figured out yet how the rest of this structure is related to the quantum Markov semigroups on M. Okay. So viewing M as an N module, you can have a basis. So you can have a module basis, and their existence in M is first proved by Pimson and Popa. So in this scenario, we call them Pimson and Popa basis, and satisfy the following two equations. Actually, given lambda extension, they're equivalent. So, and the second equation just has the implication that you can express any element in M as a linear combinations of this basis with coefficients inside M. So one of the first things that we can do, once you have a lambda extension, once you perform the Jones basic construction twice, you can define the so-called Fourier multiplier of a n bimodule map. So I have restricted to only completely positive maps, but it turns out in general, it works for any embedded module map on M. So there are many ways to define that, but in order to see why it's related to complete positivity, we have chosen this particular way to write down the Fourier multiplier. So to define this operator, we just have to define a semigroup form, and that form is defined by this formula. So for those that are familiar with the factor or the notion of confusion, you may see some familiarity here. But here the semigroup form is entirely determined by the trace and the chosen map phi. And from this definition, you can see that phi is completely positive if and only if this form is non-negative. And then so once this is non-negative, we can formulate into a positive operator called phi hat. And this phi hat will be the Fourier multiplier of phi. So how exactly is related to the Fourier matrix? Well, we have a very special element determined by the first unit projection E1 in M1, and we can just act by the Fourier multiplier on this element. Then we will have this expression here. So if you still remember the definition of Fourier matrix in the previous pages, then you'll see a similarity. At least formally, if you think of this eta j as the eij, as the matrix units, you will see a formal similarity here with the Fourier matrix. And in fact, if you choose n to be just a complex number and you choose n to be n by n matrix algebra, you will recover exactly the Fourier matrix here.
So a unique unit, like you said, phi hat is unique.
Yeah. So phi hat is determined by this pairing, and this pairing is uniquely determined by phi. So phi hat is unique. So phi hat is essentially a rather Nicodean derivative in some sense. It's defined in this way because we have a canonical inner product here determined by the trace on M1, and we're just introducing another pairing.
Do you need, like, because I also see this in the, you need like some distinguished state?
Oh yeah, good
Like,
question.
to fix
Yes, the omega is just a state given by the trace. So given by the GNS construction.
Oh, yeah.
Yeah, so that's the most natural one. And once you have another map, you can define another pair.
So essentially, right. So essentially, up to like the uniqueness of the GNS representation, this phi hat is uniquely defined.
Yes.
Given phi by this phi.
Yes, in some sense that you are absolutely correct. So the only degree freedom comes from the choice here.
Okay. Yeah. Good. Thank you.
Thank you. Right. So QFI can do more than that because the previous definition is algebraic, but with the help of finite algebra, we can turn this algebraic definition to a pictorial one. So by that I mean you can think about a planar algebra as a general form of some tensor network. So and you just pretending that this is tensor network picture, you can see that the Fourier multiplier is represented by so-called two box. So we don't call it four box because we're only counting the lines emanating from the upper line. That is two. And this I defined previously has a property that you can act by hat on M as a horizontal multiplication. which we call convolution. So, and even better than that, you can obtain phi hat directly from the representation of phi by just rotating the picture of phi 90 degrees. And you can also obtain other quantities related to phi. For instance, you can obtain the adjoint of phi by rotating the picture 180 degrees. So, and every step here, so every part of the picture can be defined rigorously in terms of algebraic relations. So it's totally legitimate for you to work only with the picture, and then you can then try to translate it back to algebras. And in fact, many proofs in our paper were first formalized by pictures, even though that may be informed, but later on they are successfully to translate back to rigorous proofs. So, so we can then begin to talk about what is the generator, like what is the formal generator of a bimodule quantum Markov semigroup. So this means that it is a quantum Markov semigroup, and at every time t, phi t is a bimodule map. So another way to say that is that the algebra N is equicoherence free for all t. And so we can first find the generator. It turns out that this generator is automatically bounded. So this is essentially because we have a finite index in inclusion. And once we have the generator here, it turns out that its Fourier transform has a very nice decomposition. So it can be decomposed further as LA plus LW, and LA is usually referred to as the Laplacian. And LW is related to the unitary dynamics. So in many cases, we can just take LW to 0 and focus on LA only. So the Fourier transform of LA has this decomposition. And if you just take a convolution of LA with some x, you will see a formal similarity between this expression and the Lindbladian. So while we're interested in quantum Markov semigroup, so one feature is that we can talk about equilibrium states and how other states is driven toward the equilibrium state. But here the situation is complicated because we also want to study this provided that we have a bimodule symmetry. So the usual the definition of equilibrium states is following. So it's very simple. You have a state. Typically, you assume that the state is faithful and normal first, and then you have some quantum channel, maybe a semigroup or maybe just a single quantum channel. You say that rho is the equilibrium of phi. If by acting on phi, if you compose rho and phi, it doesn't change. So if you think about rho as determined by a density matrix, this means that phi star acting on the density matrix of rho is just the density matrix itself. So this means that the state is fixed by the operations, and we can transform. So provided that the density operator d rho is inside n common intersect, and we can transform this definition into a picture. So on the left of this equation, we have phi star acting on rho as by convolution, and on the right hand side we have d rho itself. So this is just saying that So, yeah, so this picture is just a rephrasing of this equation. But since we have the picture itself is invariant under planar isotopic. So yeah, so we are free to rotate this zero 180 degrees and put it here, and then divide this zero back because we assumed that this row is fixed. So let's make this invertible. And then we have a potentially simpler expression. So why we want to do this? Because in the first formulation we have only a one box. So like we have one box here, we have a one box here. In the infinite dimensional case, there are many scenarios where the observable on a single line is trivial. So there's no non-trivial observable on a single line. But it may have a lot of non-trivial observable provided you have two lines. And here we can use isotopic to formulate this in terms of the relation between two boxes instead of the relation of the two box and one box. So
what do you mean by bar? D-row bar?
Oh, D-row bar means that we rotate the picture by 180 degrees. So you can think about it for a moment like we just twist that and move here to this D-row bar. Okay. So that leads to right. So by the way, this is a toolbox, but it's formed by a tensor product. So it's relatively simple because it's a tensor product between two one boxes. And this operator, it involves D-row and involves D-row inverse. So naturally, you expect that it's related to the modular operator of the state row. And that's in fact true. And it's relations like here, where the sigma row is the modular automorphism group. So in order to make, you can take a general faithful state row, and you can still try to define, maybe it's not easy to define the density matrix, but you can still define this delta row hat, provided that the Strong's projection is in the domain of the modular group. Yeah. Of the extension of row 2 and 1. Right. And in that case, there's no guarantee that this delta row head is still a tensor product of two one boxes. So it could be just any strictly positive two box. And that's why we introduced the notion of bimodule equilibrium. So it's just, so we say that this phi, it needs a bimodule equilibrium called delta hat. If delta hat is strictly positive, and delta hat E2 is equal to E2. So this E2, maybe I will use the blackboard because online cannot see it. So this E2 is the second Jones projection, and so this you can verify this condition here, right? Because the second Jones projection, when you take the multiplication, it's like you connect these two lines. But once you connect this two lines, you can slide this to the right hand side and make a cancellation. That gives you the Jones projection back. Yeah. And finally, we can, and the third condition is the picture in the previous slide. We just referred this. Okay. So obviously equilibrium states that satisfy this property gives you a notion of bimodule equilibrium.
Sorry, so I want to ask a question. So you have the Jones projections,
yes,
right?
Yeah.
And then your statement is that, like pictorially, you can have a box here and then slide it through the Jones projection, you can rotate the box. And also it's the same rotation.
Yes, it's the same. So yeah, it is.
Wouldn't that mean that you have like co-evaluation, evaluation, and
that's so. Yes, so the Jones projection is precisely a depending on how you read the picture, is evaluation, then co-evaluation.
Right.
Yes.
So would that make your N's finite dimensional?
Finite dimensional over n. N itself might not be
okay.
finite dimensional, right? So that's exactly the finite index.
So you're like these okay. So these valuation co-evaluation are defined as n by modules, is that right to say? Or
Yeah, exactly. Yes.
okay.
Wait. So let me think. Yeah. So I didn't put the two color shading here, but we are actually operating in terms of m by modules over n. Sorry, over n1. Right. Yeah, but dually you can also operate on. So like the Fourier multiplier lives in the dual of n and n, which is m1 as mn by module. So it's like, yeah, maybe. So we're talking about operators on. So this is n and n. You will put shading here, and then Fourier multiplier is like you rotate, and then you can rotate this shaded region out and the unshaded region in.
Okay.
So this is the dual. This is the duality.
Okay. Nice. Thank you.
So one wording is that this bimodule. If you recall the definition of equilibrium state, you say if rho is an equilibrium of phi, then it's automatically an equilibrium for all the powers of phi. That means that equilibrium state is stable under composition. But for bimodule equilibriums, it turns out that it's not stable under composition of quantum channels, and that essentially because this multiplication, so vertical multiplication, the horizontal multiplication, which is a convolution, that represents the composition of quantum channels, they do not commute. Yes. So by generalizing, for generalization, we lose some very nice property of equilibrium states. So to make things less abstract, we can test this definition on a very simple toy model. So this means that we choose n to be just the scalars, and m is three-dimensional ability. Yeah, and we can define basically m is the algebra of functions on 3 points, and we can define a quantum channel phi on m by a cyclic permutation. So we just permute the 3 points cyclically, like that, where this ek is, I guess, an indicator function on each point. So we can compute the Fourier multiplier, and instead we can substitute phi into this place and solve for delta. And turns out that we have many bimodule equilibriums. And if you think about a cyclic permutation on 3 points, or maybe on n points, you will see that there is only one equilibrium state, namely the weight on every point is equal, so like equal to 1 over n. This is only one equilibrium state, but we have a lot of bimodule equilibriums. So we have many more choices by considering bimodule equilibriums. And so you can see that bimodule equilibrium forms a convex set. In this case, it's not compact. But it turns out that in the same example, if you symmetrize phi, you will get a compact set of bimodule equilibriums. And of course, the set of bimodule equilibriums contains all the equilibrium states. So it seems that we have a lot of bimodule equilibriums, but what does it imply? So very nice property, although bimodule equilibrium has a drawback that it is not preserved by composition. It does help to characterize the quantum channel phi in the following way. So we can consider the fixed point set of any bimodule quantum channel, any quantum channel in fact. And it turns out that it's in general not a phenomenon subalgebra, although it's invariant algebra, but it may fail to be closed under multiplication. But so it's a very classic, very famous, it's a well-known fact, which follows from Choi's theorem on multiplicative domain, that if you have a quantum channel that admits a faithful equilibrium state, then the fixed point set is a phenomenon subalgebra of M. Okay, and it turns out that we can show that even if you don't know whether there's a faithful equilibrium state, as long as you can find a bimodule equilibrium, then the same thing holds still. Namely, that for any bimodule quantum channel phi that meets a bimodule equilibrium, you still have the fixed point still form a phenomenon subalgebra. So that I think makes the definition more interesting.
So the algebra structure of M5. So it is not Choi first.
No, it's just the original product on M. So with respect, you're absolutely right. So when given any quantum channel, given any quantum channel, you can define the Choi-Everest product such that it's the fixed points referred to which is a theta algebra. Yeah, but here I'm saying that the fixed points in general is not with respect to the multiplication of M itself. So we're not trying to modify this multiplication of M. But even just with the multiplication structure on M, as long as you can find a bimodule equilibrium, then it's still a phenomenon. So we've talked about how to formulate the so-called the equilibrium states, that is the stationary states of time evolution. And so another part of the study is that how other states converge to that equilibrium. And it turns out that in order to study, for example, in order to study the mixing time or convergence rate, you have to put additional assumptions on the Markov semigroup. So in the classical case, one assumption is called degrowth balance. So it means that this process, although globally it's not reversible because it's a semigroup, locally and in terms of probability is reversible. And this condition can be generalized to the non-commuted setting under the name JS symmetry. So by that I mean we have a faithful state rho, and we have a Markov semigroup phi p, and that phi p at every time that phi p is self-adjoint with respect to the JS inner product given by rho. So it's kind of like imposing the self-adjoint self-adjoint, so that we can use spectral theory. And one thing is that if you find a rho such that phi p is JS symmetric, then rho is automatically an equilibrium state. And so the converse is not true. In fact, if you have a equilibrium state of phi t, which is faithful, of course, and then if phi t commutes with the modular automorphism group of rho, then you can go back. You can say that then you will see that rho is phi t is JS symmetric with respect to rho. So, but now we're not even we don't plan to talk about modular morphism group. So this is just a one. So the intuition here is that by imposing GN symmetry, we can just rule out all the unitary dynamics, because unitary dynamics in general will create some circular orbits of states, and this condition is saying that there is no circular orbit in something. So in this case, one thing that we expect is if you just take phi t and push t, then this limit in whatever sense should exist. So we should be able to define this limit such that it is a conditional expectation onto the decoherence free subalgebra. Also, the fixed point is automatically subalgebra here because we have a equilibrium state rule. Okay. So we expect to have a conditional expectation. We can just sometimes repeat the previous procedure that we can leave a relation between one box and a full box to a relation between two boxes. So we still have this phi. So let's say given the state rho such that phi is GNS symmetry, we can still define these two operators. And you will see that if you translate the definition of GNS symmetry, then it becomes this equation between the two boxes. So it means that you can obtain the 180 degree of phi hat by simply multiplying delta rho bar. And then, so we can then use this definition to define bimodule GNS symmetry, and it is in fact related to bimodule equilibrium, in the sense that if delta is a bimodule GNS symmetry of phi, then delta is also a bimodule equilibrium. So it's shown in this picture. Right. So suppose delta is a bimodule GNS symmetry for phi, then this multiplication here gives you phi hat. But phi hat is uniform. So assume that phi is a quantum channel. That means that phi hat, if you take the left trace, it's identical. And this equation is precisely the bimodule equilibrium. Yeah, but unfortunately, bimodule GNS symmetry is also not preserved under composition form. So, yeah. But I think this just makes the story more interesting. And likewise, since we already have a definition of bimodule GNS symmetry for a single quantum channel, we can just define the bimodule GNS symmetry for a quantum Markov semigroup. And but here we make the slight but important modification is that we define this property only for its generator. So it's different from the requirement that each phi t is shares delta hat as a GNS symmetry. We only require that this the generator of the quantum Markov semigroup has this satisfy this equality here, and it is even weaker than the definition that for every phi t we can find a GNS bimodule GNS symmetry. So it is even weaker than that. Yes. So so in particular, by recurring this bimodule GNS symmetric property of a quantum Markov semigroup, it does not imply the existence of a bimodule equilibrium. of the full symmetry, because essentially we're just put requirements on the generator. So in that case, can we still prove that the this condition expected exists? Turns out that yes. So even though we just put the GNS symmetry on the generator, under some more restrictions, so under the condition that phi t is relatively orthogonal, this means that the fixed points of all phi t consists of only n itself. So under this additional assumption, we can still show that as long as the generator has this bimodule GNS symmetry, then this limit exists, and it's close. It's in fact very close to a conditional expectation. To the conditional expectation done. It is off by an element f phi, which is inside which commutes with an inside n. So it's almost a conditional expectation. So the bimodule GNS symmetry of a quantum Markov semigroup, even though it's a condition on the generator, it actually controls the final long term. So one additional thing that we can do for a bimodule GNS symmetric quantum Markov semigroup is that we can write down a differential calculus. So we want to do this because so in the most general setting, the differential calculus for a quantum Markov semigroup, it was first developed by subalgebra. So he thought about this from the angle of non-commutative geometry, but then later this same structure was used by Carlin and Maas to define. So in their study of functional inequalities, they used this structure to define Riemannian metric on the space of density operators on some matrix algebra, such that they were able to interpret the dynamics defined by this quantum Markov semigroup as a gradient flow. And this connection allows them to prove the generalized logs of inequality under the assumption that this quantum Markov semigroup has detailed balance. So so here to write down a similar thing, we assume that there is no unitary dynamics. So that means we consider this L0 to be L0, and L0 is the Laplacian. So that corresponds to the second part of the Lindblad form. And then we can define, so we can write down decomposition, spectral decomposition of this L0 hat delta hat to the -1/2. And this Pj will be, in general, be projections in the toolbox space. So we can write down a partial J's partial derivative, the directional derivative, as a commutator, as a weighted commutator. This weight is important to keep it symmetric. And we can sum it over J. Then we obtain the gradient. And if you because classically gradient, the adjoint gradient return to the metric will be the divergence. So you can simply take the adjoint of the gradient object and define the divergence. So in some sense, we are thinking about this finitely many direct sum of M1 as the space of tangent vector fields on some non-commutative space. So this is just an analogy, but the structure here is very much similar. So that means we have gradient divergence. And so I didn't put here, but it turns out that you can recover the Laplacian as the gradient doesn't take divergence, just as in the commutative case. Okay, so in order to talk about convergence of density operators, we need to first know where all the density operators are converging. So I mean, this is not a problem if you impose the usual GN symmetry because you already have a state. But here we are only imposing bimodule GN symmetry. That means we don't necessarily have a state on M yet. But there is a way to define such a state as a proxy of delta hat. So it's defined using a non-commutative multiplication, and it is related to given any. It is related to the initial state D with density matrix B in terms of this formula, and this formula is just saying that with respect to the Riemannian metric that we can define, this d delta is the unique solution of this equation. And this solution of this equation, also this d delta is related to the optimal transform through this equation. And we call this d delta as the hidden density of delta. So where delta hat is the bimodule GNS symmetry. And it is obtained by projecting delta down to all the gradients. Okay, so as applications, we will talk about how the previous constructions leads to the several functional inequalities. So quantum Markov semigroups it provides a natural framework to study functional inequalities, both commutative and the non-commutative ones. So in the commutative case, we have the following relation between this lots of living inequality, which implies the L2 Poynter inequality. And we also have the generalized or modified lots of living inequality. And this leads to the Calabrese inequality. And the Calabrese inequality is a transfer inequality. And in the commutative case on Riemann manifold, this implication was first proved by Otto and Villani. So this is also called the Otto-Villani theorem. So what Carlin must be is that they developed the first order differential calculus, and they use that to generalize they use that to first identify to connect the quantum Markov semigroup with gradient flow of entropy functions. And the fact they proved this first proved this generalized lots of that inequality. And they also generalized this Otto-Villani theorem. They use their non-commutative version of generalized lots of Latin inequality to prove a non-commutative version of Calabrese inequality. And so, in addition of the assumption that the quantum Markov semigroup has a detailed balance, so their methods also require the so-called intertwining property. This means that you can lift the quantum Markov semigroup by T through the divergence to a semigroup on the set of vector fields such that it is satisfying this equality. So there is a exponential decaying factor here. So that's the requirement in order to prove the generalized law of probability. And so we're able to offer a form of generalized law of probability inequality or bimodule quantum Markov semigroups that meets a bimodule GS symmetry. But of course, and also under the assumption that it has an intertwining property. So I just say that for any density operator, D is an n that we take that is taken to be the initial state. Then from the initial state, we can first find the hidden density here. And we then have that this quantity decays exponentially fast as time goes on. So this quantity at any time is exponentially suppressed by its initial value. And you can recover the generalized loss of the inequality if you take n to be C, or if you can just take this delta to be the usual GS symmetry that is determined by the state. And so in either case, you don't have this part and you don't have this part. And the first two is just the usual generalized loss of the inequality. Right. And also you have a differential form of the about inequality. So in the usual case, you do not if you do not consider the bimodule GS symmetry, just usual GS symmetry, you don't have this part. So you don't have this log B delta. And then this quantity is often referred to as the entropy dissipation. So it's an instant loss of entropy, or instant increase, rather. Instant increase of entropy as you turn on the symmetry. And our generalized loss of the inequality plays the same role as in the auto-Wielanding theorem, because we can also deduce a form of Telegram inequality in the bimodule setting. And here, so basically, you have to take care of bimodule, the hidden density once you are dealing with bimodule GS. So it is always here. And from another angle, we can also prove a Poincare inequality. But so this Poincare inequality does not require the quantum Markov semigroup to have a GNS to have a bimodule GNS symmetric toolbox. On the other hand, it requires you to take, so because we're no longer requiring bimodule GNS symmetry, we don't necessarily have a relation between L0 pack and its 180 degree rotation. So in some sense, we need to take an average. So yes. So this makes the Poincare inequality to have a, so that's related to the differential structure that we developed. Okay, so the above is basically all the topics I want to talk about today, and I want to point out two open questions for future direction. So the first thing is that we want to make a more refined comparison between bimodule equilibrium and equilibrium states. So in the simplest example, we have seen that typically there are many bimodule equilibriums that are not symmetries. But on the other hand, we find that it's very hard to define a quantum channel that has a bimodule equilibrium but does not meet any stationary states. So we want to ask whether there is this example. And if there isn't, then this means that we should be able to have some canonical construction that gives us that produces a stationary state from a bimodule equilibrium. But both questions are not solved yet. And yeah, so the next thing is about even further generalization of bimodule JS symmetry. So for JS symmetric quantum Markov semigroup, people also want to generalize the GS symmetry to KMS symmetry. So KMS symmetry, so it still implies the stationary state property, but it does not imply that the Markov semigroup commutes with the modular homomorphism. So that makes the analysis there even more complicated than the JS symmetry case. So we can also formulate KMS symmetry for bimodule quantum Markov semigroup, but we don't know yet how, under this formulation, how can we approach the functional inequality supply. So this is also a very interesting direction. This is basically all my talk today. Thank you.
Any question?
Yes. Can you come back to the first theorem about the one-man subalgebra?
So, which maybe, yes, thank you.
I guess it was the first stated as a theorem. You said the Neumann.
Okay.
Sorry.
Is this?
Yeah.
Okay.
So under which condition you get subfactor, and subfactor, and when?
Which? Okay, that's a question because of course, if you assume irreducibility, you have every phenomenon subalgebra. So okay, so first, since we're talking about bimodule quantum channel, this fixed point subalgebra it has to contain n. So it's an intermediate. So you're asking when do you get intermediate subfactor?
So here you already have a subfactor when you
No, it's in general an intermediate subalgebra. But
what is so you have the algebra M,
yes,
and the algebra M of 5.
yes.
So one is included in the other.
Yes.
What else? So is this already so in general it's not
It's also, yeah, we do not assume
what condition you can subfactor. If you assume M is a factor, then is M of 5 also a factor?
No, I don't think so.
So you don't see any condition to force that to be a factor.
I think right now I can only think about the most naive condition, that is we require n inside M as a irreducible sum. Like then automatically all intermediate subalgebras are subfactors.
So where is
other than that,
where is N here?
Where's n plays the role of decoherence free subalgebra. N, that means we n is here and we consider all the semigroups such that n is decoherence free. Yes.
So you make intermediate.
Yes.
I have one question. So you were talking about quantum Markov semigroups in GNS symmetry.
Yes.
My question is, so have you studied or have you thought about studying dilation of these quantum Markov semigroups with GNS symmetry? And those dilations will also have the GNS symmetry on them.
Dilation, you mean to dilate every psi t?
Yes.
Okay.
Satisfy certain conditions.
Oh, so this is good question. So currently we haven't considered that. So we've considered it. So yeah, I'm thinking about because in fact what Zishuo did. So how he defined this differential structure, he basically considered a dilation of the geometry instead of the whole semigroup. And through that dilation, he was able to define very abstractly a gradient. So basically derivation from n to some n bimodule. And then he defines the divergence as the adjoint of the derivation, and then he arrives at this, so this just Laplacian is equal to divergence imposed with gradient. Yeah, so, and I think you're asking about dilation for the semigroup itself.
Yes, yes.
But can you dilate all of them on a single space?
Yeah, there are certain results concerned of that, but there are no results containing semigroups with G symmetry.
Okay. And after dilation, it can still have this GNC?
No, that was one question.
Okay. Then that would be interesting because we can see whether I'm bimodule GNC after this dilation process does it meet other symmetries. Okay, that's really thank you.
So the modular, we talked about modular operator, right? This
Yes. Okay. Yeah. Right. Maybe here.
So that's I like to see that on the graph.
Okay. Yeah.
Right, so you
Can you say that?
yeah. So what happens is that
Yeah.
So the idea is that like it's an old idea by Witten. Well, I don't know how old it is, but consider like you have Penrose diagram space-time like this. And the idea is that I have an observer here and it's going to feel like some gravitational gravitons, let's say. And the idea is that, okay, I have the right Windler wedge and the left Windler wedge, and then you want to quantize quantum gravity on this kind of spatial slice. And there's a problem. The problem is that there's essentially like, let's say I say that my Hilbert space like this, and my full Hilbert space actually doesn't decompose into the right and the left. And essentially the problem is because I have a modular Hamiltonian, which is, well, okay, I'm just writing stuff down, but the idea is that I need to define a modular Hamiltonian, which is in fact inner, by conjugating with the Hamiltonian on the right minus Hamiltonian on the left. And this is, it doesn't restrict to this guy or it doesn't restrict to this guy. And there's like a thing here. So what I'm trying to say is that maybe there's some application where you found in-ground gravity in that scenario. So
okay, so I'm thinking so maybe a more maybe a simpler problem is that how this inclusion of algebras fits into.
no, yeah, exactly. Yeah. So because I was also thinking about like this condition that you had where you need the index to be, well, this guy.
Yes.
Finite. So I was thinking naively, I can think of, I have Hilbert space, I have this M, maybe I can pick the right guy to be my N. And then you can ask, okay, does it fit into your context, basically? And in that case, I will be able to think of, maybe this big operator algebra, which gets me all the field operators on Rundler spacetime. So technically, Rundler spacetime is only the right wedge, but I want to get information across the double cover, basically. But then, yeah, the idea is that, okay, if I do this, would I be able to kind of have better control or better understanding, just in general, of crumb gravity, essentially?
But I think that so from your picture, just from your picture, I think the full curve space looks more like a bimodule. So do you have a isomorphism or anti-isomorphism between AL and AR?
Anti-isomorphism. Yeah.
Okay. Then yeah.
I think time reversal is
Okay.
Yeah, time reversal is in fact one of those. Yeah. And but the thing is, like this guy, or if you take L or something, like this guy is type 3.
I
Yeah.
see. So it doesn't have a trait.
Exactly. Yeah. So like maybe picking this guy is the wrong thing to do. Yeah. But maybe there's something else that we can do. We have to use this to kind of not solve, but like to study gravity.
Just about this intermediate polynomial algebra.
Yes.
Okay, do you think every intermediate this problem? The form you what mentioned in your theorem, every intermediate polynomial algebra can be modelized of this form.
I think then right. So yeah. So you can basically if you are given any intermediate algebra, you can define a generator like that, just like the defacing or depolarizing example. So you are in this way, you are just force the fixed point algebra to be only P, right? But there are other. So this generator comes from a biproject, but there are other interesting generators that does not come from biproject.
Okay, if there's no question, let's propose talk again.